Hello, structural engineers. Here we are to the 7th appointment about the overview of my book, Computational Structural Engineering, and we left with chapter 6, which dealt with errors in a finite element calculation and all the process. And now we go through chapter 7, which deals with advanced modeling techniques, meaning that with advanced we mean, or I mean that linear codes are used to their extreme limits, so to say. And the first thing we concentrate on is the substructuring, in the sense that many codes nowadays allows the extraction of superelements, so to use the substructuring technique. But it's not said that all of them, especially the freeware or the ones which are included into CAD systems, allow to do that. So here it is explained through a simple example how to extract a stiffness matrix, so a reduced stiffness matrix to some interface point, in this case are 3, using a, so to say, manual procedure. Without exploiting the possibilities that many codes, as I said, have or give the user the techniques to extract directly the superelement. So here is explained how to do it. There is some matrix operations to be carried out or to be understood. And that's it. Then we switch to another technique. It's the submodeling. Also here, many codes allow the possibility to perform the required operations automatically. And here, once again, we see, through this simple example again, how to extract the boundary conditions to be applied to the portion of the model which is extracted from the submodel, from the global model, how to apply the proper boundary conditions. Through the usage of the shape functions. So also this example can be redone with any other code. Then still talking about submodeling, as we also see in chapter 6, we can mix different kinds of elements, which is again a sort of submodeling, in the sense that for the portion of the model where we are more interested in the stress distribution, we can use the most appropriate elements, so to say in this case brick elements, which will have all the stress components, and then use shells far away from the zone of interest. Here there are a couple of examples on how submodel has been used. This is a nacelle, which is flanged to the motor nacelle. So this is the inlet of the nacelle, and this portion is flanged to the engine support, engine case, through, as I said, a flanged connection, which is represented here by one local submodel. We will come back to this model again in the part 2 of the book. And here as well, this is an autoclave with a rectangular shape, so the chamber is a rectangular shape, not the best for pressure resisting, pressure, and for this reason we have stiffeners outside and welded connections. And here it was necessary to really have a very fine mesh to adequately catch the stress distribution, because some cracks were propagating in some of this reinforcing stuff. Then we talk about press fit connections, like a flywheel through to its shaft. And this would be domain of nonlinear calculations for contact reasons, but we can still use a linear code having a node-to-node connection, and then with some tricks we can apply the pretension, and here is explained how to extract the necessary information to be used in the finite element model. Basically, we use a thermal approach, so we expand the shaft, or we freeze the flywheel to get the wanted interference. Same example, but with a railway wheel. This is a locomotive wheel with 1,250 meters rolling diameter. Millimeters, so 1.2 meters rolling diameter. And again, to show that this approach can be exploited. For the same locomotive, we have the engine support, again with this element, tubular element, which is shrinked into the support. Then another example, still coming from railways, where these two parts of the engine cage are connected through bolts, but also some pins to withstand the shear forces, and a local model has been extracted to study what would be the condition both for the press fit and then from the force which is acting on the pin, which tends to move the two cages one with respect to the other. And here it is somehow used a sort of non-linear, hand non-linear procedure. So through the iteration of linear calculation, we come to the solution. This example and this will be repeated when we talk about nonlinearities in chapter 11. Here is also explained how to get then the proper interference values for the drawing and the part. Fatigue calculation is also shown here. And then again, something which should be solved with nonlinear codes. It's the preload of a bolted connection. So here we have a sort of tube which is flanged through 4 bolts. So we use the double symmetry, so only 1/4 of the model is built. The bolt head is simulated through MPC and the nut as well, and the beam is modeled with, the bolt is modeled with beam magnets. And also here it is shown the effect of the squeezing the gasket and the two stiffness of the gasket and the bolt and how they are combined together. Also, the bending of the bolt is considered in the FE model, of course, which is not possible to do with the hand calculations. So we show also the limit of a hand calculation which can be overcome by a linear code. And this is all for chapter 7. Next, we deal with composites. So I'm really looking forward to that, and hope you as well are looking forward to see something about composites. See you next time. Ciao!